Is time travel possible, and will it happen in our lifetime?
Well, it depends what kind of time travel you mean. It's a good question. Yes, time travel is possible into the future. A fundamental result in Einstein's theory of special relativity that he wrote down in 1905, the one from which E equals mc squared emerges, his most famous equation, is that moving clocks run slow. So quite specifically, if you're sat there in your room now where you're listening to this broadcast, or imagine us sat here, and imagine a clock flying past us, then that clock would run slow relative to us. It's not just we'd see it run slow, it would run slow relative to us. So that means that if I were to fly off now, let's say I flew off to Alpha Centauri, the closest star, or the Andromeda Galaxy, over 2 million light years away, and I flew off very close to the speed of light, and I came back again, then you would have aged far more than I would. In fact, thousands of years could have passed on Earth in the time that it took me to do my little journey. So time is, it's a famous saying, time is relative, but it genuinely is. Moving clocks run slow. That allowed you to get into the future. So you're allowed to time travel into the future by moving fast relative to somebody else. You get into their future.
Dr. Tyson, if gravitons do exist, shouldn't we be able to cancel gravity waves when putting them under close scrutiny? Can an equivalent to the double slit experiment be set up at LIGO to cancel the wave?
So the bigger story is, if you can cancel out light, such as in the slit experiment, there's a bright line and a dark line, and it's bright, dark, and bright, because the troughs add together and you get darkness, and the crests add together and you get bright, all right? They're wondering if you can take gravity, if it's a wave, cancel it out. And if you cancel it out, did you cancel out the gravity itself? That's an interesting question. Can you create negative gravity in this way? Or zero out the gravity in this way? And I don't think so.
Why are you hesitant on that?
Well, also, what LIGO is detecting is a change in the gravity, not the gravity itself. So, yeah, you can surely...
But if you can have change, then you could have negative gravity.
Yeah, in principle.
Isn't that possible?
Yes.
But we've not...
However, is it really negative gravity if it's just a part of the wave that is a trough rather than a crest?
Isn't negative gravity basically static?
I would think, correct.
Right?
Correct.
Or frozen?
Correct. And you would need that if you wanted to make a wormhole, because wormholes take negative gravity and expands holes in space-time.
Well, therefore, if a wormhole exists, then negative gravity must exist, right?
No, but you can use negative gravity. Sorry. Oh, yes. Well, I don't know. Unless aliens found another way to make a wormhole. If we see a wormhole out there, somebody discovered negative gravity. That's correct. What's more important, exploring space or fixing Earth? Let's go back to the caves, 20,000 years ago. We're all in the cave. And the lads in the cave peer through the front door, and they look out and they see mountains and valleys and hills and trees with fruit on it and the sky. And they want to go explore outside the cave. But they don't have permission. So they go back into the cave and talk to the cave elders. Back then, the cave elders would be 30 years old. Half of everyone in that day was dead before they turned 30. So let's go to the cave elders, and they say, we want to go explore outside. And the cave elder, they meet other cave elders, and they come back and conclude, no, you cannot leave the cave because we have cave problems you need to solve first. Only then can you go outside the cave door. That's what you sound like. Point is, you do both. You don't just do one or the other. You fix Earth and explore. There could be solutions out there that can help solve problems here on Earth. Unless you somehow think Earth is so big and amazing that all our solutions are contained here. But if you study the universe, this is Earth and this is the universe, and you're saying, don't study that, only study this. Then we'll solve our problems.
So you go to the end of time. And it's just like saying, why can't I escape that thing? It's like, why can't we escape tomorrow? Right, so we are going to tomorrow.
Right.
And if I said to you, let's run away from tomorrow, you'd go, I can't run away from tomorrow.
So is it the end of time because all information is being erased, so there's nothing?
Yeah, I mean,
is that the idea?
If you draw the thing, you can draw a map of it, and it just literally time ends, just purely in Einstein's theory. This is 1915. His theory of general relativity. You just get a line there, a line that says there's no future beyond this line. It just stops.
Okay.
So we think there's a lot more to it than that.
But is it just we haven't figured the rest of it out yet?
Well, that's the thing. So we're starting to get hints about what might happen, which is leading us. So to backtrack a bit, why does this calculation Stephen did? Why has it got no information? Why does it say there's no information in this radiation? The thing is, it's coming from the horizon. So it's there's loads of ways to think about it, but one way is that this weird place, this point of no return in space that you can fall through, but it's a point of no return. It sort of shakes, it almost disrupts the vacuum of space and sort of almost shakes particles out of the vacuum. That's one way of thinking about it. But this radiation is coming from the vacuum. It's coming from empty space. Whereas if you think about the thing that I throw in, if I throw this notepad into the thing, then that goes to the singularity. It's got nothing to do, the radiation's got nothing to do with this thing. This thing is not set on fire or something like that. It's gone to the end of time, and just whatever's happened to it has happened to it. So this radiation's got nothing to do with anything that falls in at first sight, at least.
If they did exist, could we contact them?
So if civilizations exist, then yes, we could. Again, the distances are important. If you think about our galaxy, it's, let's say, 100,000 light years across or so. That means that it would take a radio signal 100,000 years to go from one end to the other. So it would be a very slow conversation. Even our nearest star, Alpha Centauri, the nearest star system, with planets around it, we think, is 4 light years away or so. So that means that a conversation would take 8 years. So if you said hello, you'd have to wait for 8 years before they said hello back. And that's our nearest star system. So the distances tend to make conversation difficult.
Who do you think is the most extraordinary scientific mind that that humanity has produced?
There is no contest. Isaac Newton. Nobody comes close.
Explain why.
He, working alone, discovers the laws of motion. Then he discovers the law of gravity, universal law of gravitation. Oh, and then someone asked, Ike, or I don't know what they call him, Ike, why do your planets orbit in this shape, ellipses, ovals, rather than perfect circle? I don't know, I'll get back to you. And he goes home, and he comes back, I finally have my answer. And they said, well, Isaac, how did you do that? Well, I had to invent integral and differential calculus to answer that question. He then discovers the laws of optics, deducing that white light is composed of colors, because you could take those same colors, recombine them, and get white light, which freaked out artists of the day. So he does all of this. Then he turns 26. We have a magnetic field, and when dangerous charged particles come from the sun, we call it the solar wind, they see Earth's magnetic field, and then they channel themselves away and funnel in at the poles. And they collide with our atmosphere and render it aglow, causing the aurora. So when we see the aurora, that's the atmosphere and our magnetic field shielding us from harmful radiation. Wow. Okay. So if we lose our magnetic field, the radiation just comes straight in wherever it hits. Mars, we may have once had a magnetic field, it does not any longer. So if you pitch tent, you're susceptible to this flux of high energy particles. So she was correct to wonder, will we just have underground colonies?
Yeah.
All right. And then I'd wonder, well then, what the hell is the point of being on Mars?
But
You live underground. You live underground here.
We'll be basically the ants of Mars.
The worms, whatever. Like, what's the point of that?
Yeah.
You've seen that thing on Jupiter, that storm that never quits?
The
big red thing, the big...
Yeah, we call it the red spot on Jupiter. We call it Jupiter's red spot.
Okay.
Because that's how we roll.
That thing has been...
Spots on the sun, sunspots. See? See how...
Isn't it suspicious to you that a storm there could go on for 350 years without a break, and we never have storms that go on for 350 years without a break? We don't even have storms that go on for like 6 weeks without a break.
So, first of all, these storms are, when we have storms, it's in our atmosphere. So that's gas.
Yeah.
We rotate once a day, and so that rotation creates what we call a Coriolis force, which moving air that moves from one latitude to another, actually has its direction deflected because of this Coriolis force, and this is why storms rotate in one direction, counterclockwise in the northern hemisphere, and clockwise in the southern hemisphere. The Coriolis force is heightened if you spin faster, okay? And so what is Jupiter? It's 1,000 times bigger than Earth. It's mostly gas. And it rotates once in about 10 hours. You want to talk about ferocious Coriolis forces? We have storms that last weeks here. Hurricanes that pick up and they get weeks on this little speck we call Earth that has this much atmosphere on it. Go to a planet that rotates twice as fast, is 10 times as wide, 1,000 times the volume, and is mostly gas, and you're complaining that it lasted 300 years?
You are really good.